Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today we will discuss the backpropagation and gradient descent. Here are the contents. Training a neural network involves adjusting its weights to minimize the loss function, which measures the difference between the predicted output and the actual target. Backpropagation and gradient descent are the primary techniques that make this process efficient. Backpropagation computes the gradients or partial derivatives of the loss function with respect to the weights by applying the chain rule of calculus. Gradient descent, on the other hand, uses these gradients to adjust the weights in the direction that minimizes the loss. The interplay between backpropagation, which calculates gradients, and gradient descent, which uses them to update the weights, is key to the neural network's ability to learn from data. In this lecture, we'll dive into how each of these components works and their role in training a neural network. Neural network training follows a repetitive cycle: forward propagation, loss calculation, backpropagation, gradient descent. In forward propagation, input data is passed through the network's layers, with each neuron applying a weighted sum and activation function to produce an output. The loss function then calculates the error between the predicted and actual outputs. Next, backpropagation computes the gradient of the loss with respect to the weights, and these gradients are used by gradient descent to adjust the weights in the direction that reduces the loss. This process is repeated for each batch of data until the model converges to an optimal set of weights. Forward propagation is the first step in the training process, where the input data is passed through the network layer by layer. Each layer consists of neurons that perform two main operations. First, a weighted sum of the inputs, followed by the addition of a bias term. The result is then passed through an activation function, which introduces non-linearity into the model and allows the neural network to learn complex patterns. This process continues through the hidden layers, ultimately producing an output. In supervised learning, the output is compared to the actual target values to calculate the loss. The forward propagation step is essential for generating predictions that can be evaluated and used in subsequent updates. The loss function quantifies the error between the neural network's predictions and the actual data. It is the key performance indicator of the network, as it determines how well the network is learning. In regression tasks, mean squared error, MSE, is commonly used, which calculates the average of the squared differences between predicted and true values. In classification tasks, cross-entropy loss is often preferred, as it measures the distance between the predicted probability distribution and the true class label distribution. The loss function provides the feedback that tells the network how to update its weights. The ultimate goal is to minimize this loss, thereby improving the accuracy of the model's predictions. Backpropagation is the algorithm that allows the neural network to learn from its mistakes. It works by calculating the gradient of the loss function with respect to each weight and bias in the network. The gradients are computed by propagating the errors backward through the network, starting from the output layer and moving toward the input layer. This process involves the application of the chain rule of calculus, which breaks down the gradients into smaller parts, layer by layer. The gradient values indicate the direction in which the weights should be adjusted to reduce the loss. These adjustments are then made using an optimization method, like gradient descent, which we will cover shortly. The chain rule is a fundamental concept in calculus that allows for the calculation of the derivative of a composition of functions. In backpropagation, the chain rule is used to propagate the gradient of the loss function backward through the network. The derivative of the activation function plays a key role in this process, as it determines how sensitive the network's output is to changes in the input. By applying the chain rule, we can compute the gradient of the loss with respect to each weight, starting from the output and moving backward through each layer. This allows us to determine how each weight in the network contributed to the overall error and adjust them accordingly. Once we have the gradients from backpropagation, the next step is to use gradient descent to update the weights. Gradient descent is an optimization technique that adjusts the weights in the direction opposite to the gradient in order to minimize the loss function. This means that if the gradient is positive, the weight will be decreased, and if it is negative, the weight will be increased. The learning rate is a critical hyperparameter in this process. It determines how big each step will be in the weight space. If the learning rate is too large, we may overshoot the optimal solution, and if it's too small, the network might take too long to converge. There are three main variants of gradient descent: batch gradient descent, stochastic gradient descent, SGD, and mini-batch gradient descent. In batch gradient descent, the entire dataset is used to compute the gradient before updating the weights. While this method is computationally expensive, it's very accurate because the gradients are averaged over the whole dataset. In stochastic gradient descent, SGD, weights are updated after processing each individual data point, making the algorithm much faster but more noisy. Mini-batch gradient descent strikes a balance by updating the weights after processing a small random subset of the dataset. Mini-batch gradient descent is typically preferred in practice because it offers the speed of SGD and the stability of batch gradient descent. The learning rate is one of the most critical hyperparameters in gradient descent. It controls the size of the weight updates. If the learning rate is too small, the training process will be very slow because the network will take very tiny steps toward the minimum. On the other hand, if the learning rate is too large, the network might overshoot the optimal weights, leading to instability and poor convergence. To solve these issues, several optimization algorithms like ADAM, ADAGRAD, and RMS-prop have been developed. These algorithms adapt the learning rate dynamically based on the gradients, improving the efficiency of training and preventing overshooting. Despite being widely used, gradient descent is not without its challenges. One problem is the existence of local minima in the loss landscape. Neural networks, particularly deep ones, can have highly complex, non-convex loss functions, with multiple local minima and saddle points. This means gradient descent can sometimes get stuck in suboptimal solutions. Additionally, in very deep networks, the vanishing and exploding gradients problem may arise, where gradients become either too small or too large, making the learning process difficult. Solutions to these problems include techniques like momentum, which helps to accelerate gradients in the right direction, and advanced optimizers like ADAM, which automatically adjusts the learning rate based on the gradient's magnitude. Momentum is a technique used to accelerate gradient descent and make it more efficient. It works by incorporating a fraction of the previous weight update into the current one. This helps smooth out oscillations and slowdowns, particularly in regions where the gradient may change direction frequently. By using momentum, gradient descent can build up speed in the correct direction and avoid getting stuck in small local minima. The momentum term essentially pushes the weights in the direction that has consistently reduced the loss, allowing the model to converge more quickly and stably. In addition to momentum, advanced optimizers such as ADAM, ADAGRAD, and RMS-prop have been developed to improve the gradient descent process. These optimizers use adaptive learning rates, adjusting the step size for each weight based on the historical gradients. This approach helps the model converge faster and more reliably, especially when dealing with noisy data or sparse gradients. Among these, ADAM, short for Adaptive Moment Estimation, has become the most popular optimizer due to its efficiency, ease of use, and ability to perform well on a wide variety of tasks. ADAM combines the benefits of both momentum and adaptive learning rates. The vanishing gradient problem occurs when gradients become extremely small as they are backpropagated through the network, especially in deep networks with many layers. This leads to very slow updates of the weights, making it difficult for the network to learn. The exploding gradient problem is the opposite, where the gradients become too large, causing unstable updates and causing the network to diverge. Solutions to these issues include better weight initialization techniques, batch normalization, and the use of ReLU, rectified linear unit, activation functions, which help prevent the vanishing gradient problem by ensuring gradients are not squashed to zero. When training a neural network, it's important to evaluate the model on both the training data and the testing data. Overfitting occurs when the model becomes too complex and fits the training data too well, losing its ability to generalize to unseen data. One way to avoid overfitting is to use cross-validation, which splits the data into multiple subsets, and evaluates the model's performance across different folds. It's also important to monitor the training error and testing error to ensure that the model is not overfitting. Techniques such as regularization, like L2 regularization or dropout, can be used to prevent overfitting and improve the model's ability to generalize. In conclusion, backpropagation and gradient descent are fundamental to training neural networks. Backpropagation calculates the gradients that indicate how to adjust the weights, and gradient descent optimizes the weights to minimize the loss function. By introducing techniques like momentum and advanced optimizers such as ADAM, we can make the learning process more efficient. Furthermore, addressing challenges like vanishing, exploding gradients, and overfitting ensures the model performs well not just on training data, but on new, unseen data. Understanding and mastering these techniques is crucial for building effective neural networks and applying them to real-world problems.